Okay, the first problem is a classic example in physics of rotational motion, and that's a soup can rolling downhill. Okay, but I want to do two versions of it. Okay, one version I actually did do during the pre-recorded lecture, but I'm going to vary it a little bit, and that's different than what I did in the pre-recorded lecture. So let's read the problem and start. I have a large cylinder soup can. Okay, so you know soup cans are cylindrical shaped. Okay, and has a mass of 750 grams. I actually grabbed one of my large soup cans and saw how much they weighed. They're 750 grams. Okay, and they have has a radius of 5 centimeters. Okay, it rolls downhill without slipping and dropping a vertical distance of 75 centimeters. Okay, so four questions here. The first question is, assuming the mass, that is the mass of the soup can, is uniform, what is the moment of inertia? Okay, so that's important because the formula that I gave you for calculating the moment of inertia of a soup can is actually assumes that the mass is uniform. Okay, and just to remind you what moment of inertia is, it is related to the mass. It's how much substance is there, but it's also related to how it's distributed. Okay, so if the mass is all very close to the axis of rotation, then there's very little moment of inertia. But if the mass is far from the axis of rotation, then there's a lot of moment of inertia. And that's because moment of inertia is a measure of how hard it is to get something turning. Okay, so like ordinary mass is like how hard does it get it accelerating. That's what F equals ma is all about. And moment of inertia is how hard is it to get it turning. That's what tau equals I alpha is all about. Okay, so let's start off here. So assuming the mass is uniform, what is the moment of inertia? Well, the formula for that is pretty easy. It's this one right here. Okay, and oops, where do I have my answers? I'm just going to cut and paste my answers as I usually do, so I don't make a mistake. There we go. Okay, that worked. All right, so that's the formula right there. Now, there are different shapes, okay, that you could use. There's like a ball, a sphere, okay, a solid sphere. And what were the other shapes we did? A rod, okay, a rod, and things like that. But here we have a cylinder. And if you look, you say, well, I didn't give you a cylinder, but I did. It's actually a disc, okay? So a disc, usually you don't worry about the thickness of a disc. You say, but the height of a disc, it's like very thin, but it's got a radius because it's round. All right. But a cylinder has a height. Doesn't matter. The height of the cylinder doesn't matter. It's purely the radius. So the moment of inertia depends only on the radius of the cylinder, provided the cylinder is rotating around an axis through the middle. Okay. Like I showed you in the pre-recorded lecture. Okay. In that case, the moment of inertia is given by this formula right here. 1/2 mr squared. Okay, they all have the formula or the structure mr squared or ml squared, depending what you're measuring. It's that factor out in front that's different. So if this were a sphere, that would be 2/5 instead of a half. Okay, but this is all of the tests were open book. The last test is going to be an open book test, so you could just look up that formula at the time. But still, you need to know to match the shape to the formula. Okay, and so because this is a cylinder has the same moment of inertia as a disk because the height of the cylinder doesn't matter, only its radius. Okay, and so that formula is 1/2 mr squared. Well, the mass is 750 grams, and whoops, point. I did calculate it right. I just forgot to put the point. 0.75 there. Okay, so there's the 1/2. All right, so 1/2, zero point 0.5. The mass is 750 grams, but we got to convert to kilograms. So that's 0.750 kilograms. And the radius is 5 centimeters. Converted to meters, that's 0.05 meters. And let me just quickly make sure that I did that right. I'm pretty sure I did, because I can just see from the answer that it looks right. But might as well check it to make sure. And 0.0009. 0.0009. Yep, that's right. Okay, so there it is. It's actually a very small number, and so you might want to write it in scientific notation, which is 9.375 times 10 to the minus 4 kilogram meters squared. Okay, now what's making this number small, okay, because like 10 to the minus 4 is 1/10,000th. Okay, so this is like 9/10,000ths of a kilogram meter squared. What's making the number small is not so much the mass, but the radius of the cylinder. Okay, but there it is. That answers the the first question. Okay, so assuming that the mass is uniform, in which case that formula holds, what is the moment of inertia? And the answer is that right there. Okay, so let's see if there's any questions. Oh, okay. Next, how fast is this can moving when it gets to the bottom of the hill? Now, I actually did solve this problem, but when I solved it in the pre-recorded lecture, I just did it generically, okay? In other words, I didn't use any numbers. We don't have to go through all those steps. You can go directly to the formula that I derived there, and that formula was this one. Let me cut and paste it. It was this formula right here, okay? So I say a drum, but I should just say a cylinder here, like that, okay? So for a cylinder, it turned out that the when it rolls downhill without slipping, so it's actually going to start rolling downhill. When it gets to the bottom of the hill, it turns out that its velocity is related to the height, the vertical drop. That makes sense because this is a conservation of energy problem, okay? But that number there, that 4/3 that you see in there, this depends on the geometry, like whether it's a sphere or it's a cylinder or whatever. Okay, and the reason is because that geometry will make a difference between how much energy goes into purely translational, that's the 1/2 mv squared, and rotational, 1/2 I omega squared, and different shapes. The distribution of the energies when it gets to the bottom are different. Okay, now you'll see that in the next part. So if you didn't quite understand what I just said, hang on and you'll see what I'm talking about when I get to the next one. But since I derived this formula, there's no reason to go through that derivation again. You could just use it. And so this formula here, velocity is equal to the square root of 4/3 GH. That's for a cylinder that drops down vertically h, okay? And then g, of course, is 10 meters per second squared, okay? So if you have a vertical drop, a cylinder rolls downhill, and the vertical drop rolling downhill is h, you can use this formula, okay? So I just plugged in the numbers. For G, we're using 10, and the vertical drop I said here is 75 centimeters. Okay, so it drops 75 centimeters, and that gives you that the velocity of the center of mass when it gets to the bottom of the hill is 3.16 meters per second. Okay, so that's how fast it's rolling. Okay, now when it gets to the bottom of the hill, it's actually doing two things. It's not only is its center of mass moving, but it's also rotating around the center of mass because after all, it's rolling. Okay, but I did say how fast is it moving. I could have also asked what its rotational or its angular velocity is at the bottom, but that's not, I think, as interesting as just how fast is it moving. Okay, now the next problem, part C, you can't do what you can't use one of the pre-derived values like V is equal to 4/3 GH. Okay, and the reason is that I'm going to say that we're going to assume that the mass is not uniform. Now, if the mass is not uniform inside of that can, okay, like maybe you have chicken noodle soup or something like that, all right, and I don't know, the middle of it is more liquidy than the outsides. I mean, there's lots of reasons why the mass may not be uniform, okay, and in that case, this formula right here, okay, for the moment of inertia may not apply. Okay, in fact, there may be no formula that applies because it could be that complicated. That formula there from the moment of inertia, when used with the conservation of energy, that's what led to the 4/3. Okay, so I'm not going to repeat that right now, but this formula here follows from that one, and that's only going to be true if the mass is uniform. And here the mass is not uniform. Okay, and so let's see what I'm asking. So I say assume the mass is not uniform. Oops. Assume the mass is not uniform, and that the moment of inertia is actually 5 times 10 to the minus 4 kilogram meters squared. So if we look at what we got above, here we got 9.375, like 9 times 10 to the minus 4. And here it's like 5 times 10 to the minus 4. So it's a different number. It's less, okay? A little bit more than half of what it was above, okay? And that's going to change the distribution of energy between the translational, the 1/2 mv squared, and the 1/2 I omega squared, okay? So let's do this problem, all right? And for this problem, we have to use conservation of energy. In other words, you got to repeat what I did in that derivation. The derivation that I did to get to this formula here, we have to repeat for part C. Okay, so what does that look like? Well, it's conservation of energy. And so here, let me just cut and paste the whole thing. I think I'm cutting and pasting too much, but that's okay. go through it. All right. It is conservation of energy. Okay. And so when it's at the top of the hill, all right, I guess I didn't say it, but let's assume that when the can is at the top of the hill, it's not moving. Okay. So it's not moving. And if it's not moving up there, the energy is all potential energy. All right. It's at the top of a hill. And so potential energy, that's going to equal mgh. Okay, there's no kinetic, so I didn't add it in there. All the energy is potential energy, mgh. This is exactly like the energy problems we did, with like roller coasters going downhill. And even though it's going to be rolling at the top of the hill, it isn't rolling, it isn't moving at all. It's just sitting up there until maybe I give it a bit of a nudge. And so all of its energy is going to be potential, and potential energy, mgh. Okay, gravitational potential energy. All right, well, substituting in the numbers, m is 0.75, G 10, okay, and then the height is 75 centimeters or 0.75 meters. That turns out to be 0.5625 joules, okay. So all through the motion, at the top when it's just standing still, when it rolls downhill, and then when it gets to the bottom and it's rolling as fast as it's going to be going, all of the energy remains a constant 5.625, okay, joules, okay. Now, in these problems, there's a tiny bit of friction so that you get rolling, but not so much friction that you're losing energy, okay? Because you're not really sliding across the surfaces, so you're not producing heat. That's what's going on there. Rolling requires friction, but rolling is a way of having friction, but not having the energy dissipated through the friction, if that makes sense, okay? And that's what the brilliance is of the invention of a wheel, because you're not going to get rid of friction in the real world, okay? Like, our roads are not they're not linear tracks where things float on top. There's a lot of friction between the tire and the road. But that friction doesn't matter because the tire isn't sliding across the road producing heat. It's just touching it. Okay, and that's why rolling is a very interesting phenomenon. Okay, anyhow, bit of an aside. So there's the energy. Now, when it gets to the bottom of the hill, the energy is all kinetic. So there's the formula there. And there are two pieces. Why? Because now this is an extended object. And as an extended object, it's got a center of mass, and the center of mass has a kinetic energy associated with it. And that's exactly the same as the kinetic energy that we looked at earlier before we did rotational motion. That's just 1/2 mv squared. That v there in that formula, that v is the velocity of the center of mass. Okay, so this thing is moving, the center of mass is moving with some velocity v. It has some mass m, and so it has an energy 1/2 mv squared. But that's not all of the energy because it's also spinning. And anything that's spinning has rotational kinetic energy, and rotational kinetic energy is given by the formula 1/2 I omega squared. Okay, so there's the other piece to it. Okay, that 5.625 joules, some of it goes into this energy here, translational kinetic energy, and some of it goes into rotational kinetic energy. Okay, and how much of it goes into one and how much of it goes into the other depends on how big I is. Okay, so that's what I was talking about above, that the energy, it goes into both translation and rotation, but the distribution, like how much goes into translation and how much goes into rotation, really depends on I. Now, if you have a formula for I, like we do here, okay, you could just plug it in and then you get this for your final answer for the velocity, but we don't. Okay, and so that's why where am I? Right here. That's why we have to reproduce everything that I did in the pre-recorded lecture, but we have to do it in general for just a general value of I. Okay, and then the only other thing that you need to know, so one thing you need to know is that the energy is both the kinetic energy is both translation and rotation. The other thing you need to know is this formula right here, and that's the formula that relates the velocity of the center of mass to the angular velocity. Okay, and that's the condition for rolling. Omega is equal to v over r. Okay, so with that, let's solve the problem here. So energy is conserved. So the energy after and the energy before are the same. There's the 5.2625. Okay, so I put that in there. All right, and there's the 1/2. The mass of this thing is 0.75 kilograms. And I'm asking for the velocity. How fast is it going at the bottom of the hill? So we don't know the velocity, so we just leave that alone as v squared. Okay, plus 1/2 I omega squared. Here's the 1/2. Okay, I Well, I now you can't calculate from a formula. I just gave it to you. There's the I. Okay, it's 5 times 10 to the minus 4 kilogram meters squared. Okay, so we're just going to put that in there. All right. And you probably don't remember what I did at this point when I did the derivations in the pre-recorded lectures, but I put a formula there. Okay, instead of putting a number, I put a formula, and then I derived a formula for V. Okay, but here I give you I, and in fact, I said, you look, there's no way you can calculate the moment of inertia because it's a complicated system. Okay, the mass is not uniform. As soon as the mass is not uniform, you're going to have to say, well, geez, how would I even work out that I? Okay, and in general, you can't, because it might be too complicated. I just gave you the value of I. Okay, maybe we found it experimentally. All right, and then for the angular velocity, well, I don't have V, but I do have the radius. The radius was 5 centimeters, so it's 0.05 meters there like that. So instead of omega squared, I've got V divided by 0.05 all squared like that. Okay, so make sure you understand what I did up to here, because I think this is substituting in the numbers. It's not just substituting in the numbers. You have to really know what's being asked for. Okay, so when it's asking for the angular velocity, you don't really have that angular velocity. What you have is the velocity of the center of mass. Well, you don't have it, but you want to find it, and you have the radius of the rolling object. Okay, so when you go to put in that omega, you don't put in omega. You're going to put in V divided by R. Okay, R you have in the V you don't. All right, so now from this point on, it's just a matter of isolating V. So still 5.625 is equal to, that works out to 0.375 V squared there. Okay, plus this works out to 0.00025. Okay, V squared is V squared, and then divided by zero point 0.5 squared like that, 0.05 squared like that. Okay, now we can simplify this a little bit more because we can divide that by that, and that turns out to be 0.1. So now we have that the total energy 5.625 is equal to the first term, the translational kinetic energy, plus the second term. Okay, now V is the only thing that's unknown, so V is unknown in both of those terms. You can collect them together, 0.475. Okay, and then divide and then take the square root, and it turns out that the velocity at the bottom of the hill is 3.44 meters per second. Okay, let me see if there's any questions in the chat. I agree that this is kind of a complicated problem, so that's kind of why I dropped it out of the assignment. I said let's do it together so I could explain what's going on, and well, there it is. Okay, so let's compare this number here to the previous one. So in the previous one, you had this soup can, okay, and maybe it's like cream of mushroom soup, which is solid. Okay, it's like when you rotate a cream of mushroom soup can, and like everything inside of it rotates. Okay, and unlike chicken noodle or broth or something like that, where the outside might rotate but the middle doesn't. Okay, because it's more fluidy in there. All right, so in the case of the very solid can of soup, we found out that the velocity at the bottom was 3.1 what was it, 3.16 meters per second. Okay, so 3.16 meters per second. If the moment of inertia is a little bit less, notice what the velocity is now. Now it's 3.44. In other words, it's moving a little bit faster at the bottom of the hill. At this point, you say, well, that doesn't make sense. I mean, why would it be going faster at the bottom of the hill? The translational motion is faster, but that's because there's less energy in rotation. There's more energy in moving. Okay, translating it. Translation just means like moving it from one side to the other. Okay, like moving it like across the ground. Rotation is of course around the axis. Okay, so there's more energy. The smaller I is, the more energy there is in actually it moving translationally than in rotating. Okay, so that's what's going on, and you can actually show this. Now, there are YouTube videos, and you know what? In retrospect, I should have probably prepared one. They're all over YouTube. You know, this is a classic experiment. You take chicken noodle and you take cream of mushroom and you roll them downhill, and sure enough, the chicken noodle gets to the bottom before the cream of mushroom, and this is why. Okay. All right. So the last one, and I did cut and paste too much, but that's okay. I'll just move it out of here to here. the last one says assume whoops, okay. Assume that the can slides downhill without rotating at all. Okay, so the details of how the sliding is happening doesn't matter. There's just no rotation at all. Okay, so if there's no rotation, your energy, your total energy at the bottom is purely translational kinetic energy. There's no 1/2 I omega squared. So above we had 1/2 mv squared, but then in addition to that, we had 1/2 I omega squared. But now, if like, and omega is like the rotating, how fast is it rotating? But I just said it's not rotating at all. Rotating. Whoops, forgot a G there. There we go. It's not rotating a lot at all. So this time when you get to the bottom, it's purely translational kinetic energy. And I say, how fast is it moving now? Okay, it's being clipped here. There we go. How fast is it moving now? And the answer is even bigger. Okay, so the total energy, it's still that 5.625 joules is equal to 1/2 mv squared. Okay, 1/2 m, that's like 0.375, and the only unknown is v. So solve for v, and it turns out to be 3.87 meters per second. Okay, so if this can were to go downhill, dropping a vertical distance of 75 centimeters, and it's like perfectly smooth, so it doesn't rotate at all. Well, if it's not rotating, the rotational energy doesn't siphon any of the energy away from translation. That means it's translating faster, which means that you have a faster velocity, and you can see that instead of like before when it was rotating um, a little bit sloshy but still rotating, you had 3.44 meters per second. But now when there's no rotation at all the energy goes into translation, and you have 3.87 meters per second. Okay, so well, there's an example of the energy problems. Okay, rotational energy problems. Now, one last thing, in the pre-recorded lecture, I did, a cylinder going downhill, a ball going down, a sphere going downhill, and so on. And if I ask a question like that on the test, there's no reason why you can't use the corresponding formula. Okay, so why not? I derived it for you. Use the formula. But if you're in a situation where you don't really have like a solid um, material, or the I is different than the value for a sphere or cylinder, and you might say, well, why would the I be different? Because the mass is not uniformly distributed, and so those formulas don't hold. Well, in that case, you have to go back and just redo the whole energy analysis from the beginning. Okay. Now, you might say, geez, this is really hard. Like, why do I, as an ESS person, have to learn this at all? Well, we're talking soup cans, but the human body is made up of segments, like the arm and things like that. Okay, and or the forearm. Okay, and each one of those segments can be treated very much like a cylinder or something. Similar, like the shapes that I have. Okay, it's not exactly a cylinder, because it's thinner up here than there, my forearm. But roughly speaking, you can. Okay, but we know what the moment of inertia is of the forearm. Okay, I mean, if nothing else, people have done dissections on humans like we do in our gross lab or whatever. But we kind of know what the moment of inertia are of various segments of the human body. And if you're talking about the energetics of the human body and rotational motion, this kind of physics applies. Okay, so that's why I wanted to do a problem like this, a little bit more sophisticated than just plug in the numbers, and where you had to actually do an analysis and rethink the energy. Well, there it is. Okay, so if you ever go into any kind of kinesiology, you'll probably really have to rethink the energetics for each of the pieces, and so that means you have to go back to the fundamentals, and the fundamental is conservation of energy. Okay, well, there's our first problem. Let me see if there's any questions in the chat there. No, you guys seem to be okay. And so let me go on to our second problem, and I'm only going to do two problems today. Okay, there wasn't need to do more. Okay. All right. So merry-go-round. All right, and I talked about that in our pre-recorded lecture. Let me just show you what I mean, okay? Because I try to give a description of it, and because usually when people think of a merry-go-round, you think of the horses, but there's also this thing. Let me just see if I can bring up the picture, or sometimes called the carousel. Okay, there it is. So you can see there, like when I was a kid, I used to love playing on these things because you'd make them spin very, very fast, and it was, it was always a lot of fun. Okay, and so I'm sure you've seen them. They also go by the name of carousel and merry-go-round, but they're not the kind of like with the horses that bob up and down. Okay, guess these are the kind of like manual ones. Okay, so my next problem, I'm going to actually have a merry-go-round like that. All right, so I've got a merry-go-round, and it's made up of a circular disc of mass 75 kilograms and radius 1.5 meters. Okay, that looks about right for that what we just saw there. It looks like it weighs about 75 kilograms. That would be like 150 pounds, something like that, and a radius of 1.5 meters or 3 feet. Okay, rough. Well, no, not 3 feet. It would be 4 feet. Okay, it's 4 feet. Okay, so that sounds about right. Maybe a bit more. I don't know, but there it is. Okay, and the merry-go-round is initially at rest. Okay, so it's just sitting there, and a child that weighs 50 kilograms, about roughly 100 pounds. Okay, 50 kilograms is running at 6 meters per second. Okay, which is a pretty good pace, and then jumps onto the edge of the merry-go-round. Okay, and I want to know how fast is the merry-go-round and child going to be spinning after the child jumps on. And I think you can imagine what's what would happen here. The merry-go-round standing still, but once the child jumps on and grabs hold, both the child and the merry-go-round are going to go around in a circle like that. Okay, and I've kind of got a picture from above, so let me switch back here and let me switch to my other image. How do I switch to my, there we go. Okay, and so not the best diagram here, but here we're looking down from above. Okay, and this arrow right here, this is the child running and landing on the merry-go-round. The radius here, like that radius there, I said was 1.5 meters, like that. Okay, and the mass of the merry-go-round, I said, what did I say? It was 75 kilograms. Okay, and the child here, that big dot there is the child hanging on. The child there had a mass of 50 kilograms, like that. Okay, all right, so well, that's the setup. What am I asking? I'm asking how fast are they spinning? Okay, so this one is kind of like the very last problem I did. And there in the very last problem is I had a rod that was kind of like like kind of like this. It's like just hanging from there like that, and it could swing like this. Okay, and then a bullet comes by, and the bullet lands and embeds itself, and of course, once it does, this thing spins. Okay, it's the same thing. You can say, well, what principle is being conserved here? And it's angular momentum. Okay, and I do have an angular momentum problem on the assignment, which is similar to one in a pre-recorded lecture, but I wanted to do this one because this one tends to cause a bit of confusion, because when the child is running, we could go back to that diagram again. When the child is running, you see here how I have this straight line. Okay, let me actually highlight it in red here. That straight line. You say, well, does that child there, when they're running along the straight line, do they have an angular momentum? Because angular sounds like you're going in a circle. And they definitely have a linear momentum, but what's the relationship between angular momentum and linear momentum? And that's not at all an easy concept, okay? Basically, if you take any linear quantity and you divide it by r, the radius, you get the linear value, okay? Or so, if you have the linear value and divide by r, you get the angular value. Okay, and then the converse is if you have the angular value multiplied by r, you get the linear value. And so there's an equivalency between angular momentum and linear momentum, all right? And that's what we're going to use to do this. We're going to think about this problem in terms of angular momentum, although we could do it in terms of linear momentum. Let's think about it in terms of angular momentum, because that's the way I did it in the pre-recorded lecture. Okay, so let's start off here. I'm going to just cut and paste the entire answer. Like this. Okay, so angular momentum is conserved, right? So it's conserved quantity. So what is angular momentum? Angular momentum is given the symbol L. It's usually given a scripted L. In my freehand notes I could do it, but here I have to just do a capital L. I don't know why. I don't know what the history is, but capital L is the symbol for linear momentum, and it's simply equal to the moment of inertia multiplied by the angular momentum of the entire system. Okay. Now, if you have several objects, you would just do I omega for all of them and add them up. Okay. So there it is. All right. Now, before the collision, the angular momentum is purely due to the child. Okay. And the reason is that the merry-go-round isn't moving at all. Okay. So it's not rotating at all. All right. And so it has no angular momentum. The child, you would say, well, the child isn't rotating. Yeah, but the child is moving. And at the moment the child actually jumps onto the uh, carousel, merry-go-round, jumps on, even before grabbing, you could think of the child as having an angular momentum at that moment. And that seems a little bit strange, but here's why. Let's go back to this picture again, okay? And if you take a look here, we're looking right here, right there, like that, okay? Right at that point, just before the just as a child is jumping on, but before the merry-go-round actually starts to rotate. Well, at that point, the child has a velocity of 6 meters per second, all right? And the child is at a radius of 1.5 meters, okay? All right. Not here, like out here, you say, well, that's definitely more than 1.5 meters. I know. But right at the moment that the child is jumping on, the radius is 1.5 meters. So you have not only a velocity, but you have a radius. And then you can say, oh, well, the angular velocity is just the linear velocity divided by r. Okay? And this is the formula that does the conversion between the linear and the angular quantities right there. Okay, so having said that, now we can go ahead and calculate this quantity here. Uh, Omega, well, I guess I should have done that first. It doesn't matter. Omega is V divided by R for the reasons I just said, okay? V is, as the child comes in, 6 meters per second. R is 1.5 meters, okay? The child is grabbing onto the end of the merry-go-round. And 6 divided by 1.5, that's going to be 4. So the angular velocity of the child, uh, just as they're about to grab onto the end of the merry-go-round, is 4 radians per second. Okay, 4 radians per second. All right, so that's this one here. Okay, now that's the moment of inertia of the child. And again, you go, geez, how's there a moment of inertia to a child? Well, let's go back to this picture. The child here. So what's moment of inertia for a point mass? The moment of inertia for a point mass is, you remember, there's moment of inertia formulas for cylinders, for spheres, for rods and things like that, but there's also just moment of inertia formulas for a bunch of point masses that are at some radius, and that's mr squared. Now, like if you've got something like a dumbbell, you might have mr squared for one mass plus mr squared for another mass plus mr squared for another mass, but here we have just one mass associated with the child. Okay, so there's the mass m, there's the 50 kilograms right there. And again, at that instant when the child is about to grab on, they're at a radius of 1.5 meters. Okay, and we want to square that. And if we multiply that together, those two numbers together, like that, 50 times 1.5 squared, that's your moment of inertia of the child, okay? Again, it's kind of weird because we're not asking what's the moment of the inertia of the child here or there. We have to think about it right at the instant when they're about to grab on. And at the instant when they're about to grab on, it's mr squared, 50, 1.5 squared, okay? So a bit of a mind twister because, you're really concentrating on calculating omega and calculating I at that instant. But still, it's perfectly legitimate because it's a conserved quantity. So it doesn't matter where in the motion you calculate it, you should always get the same value. All right, so what's that? So mr squared, well, that's 50 times 1.5 squared, and that gives you 112.5. And the units for I are kilogram meter squared. There's no abbreviation for it. It's just kilogram meter squared, okay? So there it is. There's the moment of inertia of the child, okay, the I for the child. And so if you just do angular momentum is I times omega, that's 112.5 times 4, or 450 kilogram meters squared per second, okay? And you might say, what happened to the radians? Because if you take a look here, I has units kilogram meter squared, and omega has units per second, there like that. But there's also the radians in there, and I dropped them out. And if you remember, radians are really not they're not a unit because they're always formed as a ratio of two lengths. Okay, so if you've got a length divided by length, the lengths cancel out, and that means dimensionless. Okay, so radians, we usually write them in there just to remind you that this is about rotational motion. But if I had written here instead of um, 4 radians per second, if I'd written 4 per second, it would be just it'd be just as good. Okay. So all right. Let me see if there's any questions so far, because I admit these are conceptually a little bit more difficult. Okay. Uh, all right. Well, that's the before. And the after, well, that had better be conserved too. But after, what do you have? You have the combined child plus merry-go-round. Okay, and so you have the angular momentum after is the momentum of inertia after, and the angular velocity after. Okay, now we don't know the angular velocity after because that's what I'm asking you. I'm asking you how fast is the child plus the merry-go-round spinning afterwards. Okay, so that's actually what we're trying to find. We're trying to find that omega primed, and the primed here meaning after the collision. Okay, after the child grabs on. Okay, it's the I after that's different. Okay, so what is that I after? Well, just ask yourself, what is spinning after the child grabs on? Not just the child, but the child and the merry-go-round. They're both spinning together. Okay, so this new I here, this new moment of inertia, is the combined combination of the two. We already have the moment of inertia for the child. What we need is the moment of inertia for the merry-go-round. Okay, and the merry-go-round can be treated like a disc. Once again, the thickness of it doesn't matter. It's just how is the mass distributed radially, not height-wise. Okay, so it might seem strange. We're going to use the same formula that we did for a soup can a minute ago, and you say, well, a soup can doesn't look anything like a disc, but it does, because if you take the soup can and you squish out the height, it's a disc. Okay, and that's all that really matters, is just like how far the masses are from the middle, from the axis, not how far along the axis. Okay, so it's the same thing for a disc or for a cylinder, same formula. And so we're doing the merry-go-round. So the merry-go-round, there's the half. That factor half is because it's a disc. Mass of the merry-go-round was 75, and its radius is 1.5, and that turns out to be 84.375 kilogram meters squared. Okay, now that isn't this I primed, because that I primed is both the child plus the merry-go-round. Okay, and the child here, that's we have from above here, is 112.5. Okay, and just again, we treated the child like a point mass at a radius r, and we got a moment of inertia of 112.5. And the moment of inertia of the merry-go-round is 84.375. Okay, and that turns out to be this number, or rounding it off, 197 kilogram meters squared. Okay, so now we can plug into this. All right, and the moment of the angular momentum before and after are the same. Okay, so we found the angular momentum was 450, so it's still 450. Okay, it's conserved. And moment of inertia, the total moment of inertia of everything that's rotating, that is both the child and the merry-go-round, 196.875. Omega is the only unknown. Solving, we get 2.28571 radians per second. And I didn't round it off. Okay, now this question is a little bit ambiguous. I would be very careful on a test. Okay, I said, how fast is it spinning afterwards? And you go, well, what is he really asking for? Is he asking for like how many revolutions per minute? Is he asking for tangential velocity? So I would be a lot more specific on a test. Okay, so omega primed in radians per second, I guess that's fine for how fast it's spinning. The next question is, what's the tangential velocity? Okay, so let's work that out. And you just saw a minute ago that you equate the linear and the angular quantities by a factor of r. So here we have the angular. How do we get the linear, which is the tangential velocity? You multiply by r. Okay, so there's that. Sorry, phone call. There we go. All right. So the tangential velocity is equal to the radius times the angular velocity. We just found the angular velocity to be that 2.28. Okay. So there it is. 1.5 times 2.28571. And that turns out to be a tangential velocity of 3.43, rounding off 3.43 meters per second. Okay. So the child on the edge, or any point on the edge of that merry-go-round, is going to be moving at 3.43 meters per second, okay, after the collision. So, always look to make sure that does your answer make sense? Okay, does your answer make sense? So how fast was the child running before they jumped on? Well, before they jumped on, the child was running at 6 meters per second, okay? And then after they jump on, they're still moving, okay, albeit on a curve, they're still moving, but now they're moving at a velocity of 3.43 meters per second. And that makes sense. You don't expect the child to jump on and then suddenly it spins faster. You expect the child to jump on and then the child is moving slower along the circumference of the merry-go-round. Okay, and that's what you found. All right. So yeah, it does make intuitive sense. All right. So there's that one, and one more question, and then we're done for today. Okay. And the last question was, how much energy is lost during the collision? It is a collision. I mean, usually we have pictures of collisions of like cars colliding and things like that. But even things, coming together and sticking in physics, we call that a collision. So this is a collision, and it's an inelastic collision. You know that because whenever we did the linear momentum problems, whenever things stuck together, the energy always decreased afterwards. And here these two things are sticking together, so energy is going to get lost. And so let's work that out. All right. So what's the energy before the collision? Well, the energy before the collision is purely the child running. Purely translational kinetic energy, okay? And there's no potential energies in this. No one's going uphill, downhill. There are no springs or anything like that. So purely the child is running. And so with that translational motion, you have a kinetic energy of just 1/2 mv squared. No 1/2 I omega squared. There's no rotation, okay? And so, half child's mass is 50, and the velocity before the collision 6 squared, like that. Okay, for a total of, or a value of 900 joules. Okay, so that's how much energy the child has running up to this merry-go-round. Jumps on, grabs hold. Now what's spinning? The whole thing. Okay, there's no translation now. Okay, I know the child is moving around the outside, but now you can think about the child as rotating about an axis. So the child is rotating about this axis, and the disc is rotating about an axis. That is the axis of the merry-go-round. And so now you could say, oh, all of our kinetic energy, it's now all rotational kinetic energy. It's the rotational kinetic energy of the combined child merry-go-round system. Okay, and so it's just 1/2 I omega squared. All right. But I now is the I of the combined, it's after the collision, so it's the moment of inertia of the combined merry-go-round child, which we found above to be 196.875, okay? And the angular velocity, omega prime, we found to be this value up above, 2.28571, like that. And of course the omega comes squared. Okay, so there it is squared. And if you work that out, you find that the energy after the collision is 514. So before it's 900, after it's 514, and you should say, yeah, this is making sense. Okay, why is it making sense? Because you wouldn't expect the energy to go up. It's an inelastic collision. When things stick together, it's inelastic, and so you expect the energy to go down, and it did. And in fact, if you calculate delta E, the energy decreased by 385.7 joules. Okay, so there you go. There's the energy expended and the child grabbing on. You might say, well, where is that energy, after the child grabs on? Well, not sure. It'd probably be in heat or something like that. Okay.